That's what it is. Okay, that was like. All right, sorry about that. It's recording. I'm gonna switch over to the whiteboard. All right. Here we go. Right. Everything should be good. All right. So today we're gonna, we did the XOR problem last week, right? And we finished it. And you guys have a homework assignment. I think you saw it, right? Basically convince yourself about neural network, right? So follow the instructions there. So just kind of quickly on Brightspace, I posted some papers, right? So you can go to Brightspace and they are under the universal approximation theorem, okay? Now, these are papers that they're only just for your own information, right? If you are very curious about this, right? But basically, they're the classic papers in the literature related to neural networks, which basically, I kind of alluded at this, they're the seminal papers, right? So they're the ones that say and prove that neural networks are universal function approximators under like some math conditions, but in general, right? There's always some exception to everything, right? But in general, these basically prove that the neural networks can learn. Let's not say everything, every function in the universe, but a lot of them, right? A lot of very significant ones. All right, so these are the papers that go into all that theory. Okay, and you can if you have an interest in this, you can read through them. Okay, but I leave that to you. I mean, they're pretty interesting, I should say, and because today I'm going to talk about history anyway, so they're historical in that sense. There's Wikipedia, and then the 1989 paper, which is the paper, and then there's like the papers Resness and the 2017 paper. So they're there for you. Okay. All right. And then, that's it's all kind of summarized, but I'm showing you where they are so you can click on them. Oh yeah, let me switch back. All right. So yeah. So here we are. So today I'm going to talk about history, right? Remember what I said? I like this part actually. It's very interesting. So I'm talking, and it's always good to put context into everything, right? And the history gives it a little bit of context. Basically, the papers, what they say is that neural networks can approximate any function. And so when I say a neural network, right, you got something like this with an activation function, right? And like that, right? And it has actually been proven. A lot of people are careful here, and they say that probably a network with an input layer, a hidden layer, and an output layer with an activation function can approximate any function, basically. However, other papers are a little bit more careful in saying that at least 2 layers. Okay, the 2017 is more careful in their language. All right. But basically with this, you can, in theory, so what this is saying is any network like a CNN or a ResNet could be done just with one input layer, one output layer, and let's say at the minimum of 2 hidden layers with activation functions. In theory, it could. What's the problem, though? That the number of neurons here would need to increase. So it's the difference between depth and width of the network. So depth would be in that direction and width would be in that direction. Do you guys see that? So I gave the example on Thursday, I think, of a network such as this, where you have three So that's a deep network, right? So it's got an input layer, an output layer, and then hidden 1, hidden 2, hidden 3. And I said this can be, in most respects, equivalent to one that is like this, but where these 3 become 1. So let's say this is A, B, C. So then A, B, C, and the output. Do you see that? So then you might ask yourself, well, if there are theorems that say that this is possible, then why do we need deep learning? Because we could just do everything with a network such as this, which only has one hidden layer. Do you guys get the idea? And although the theorems say that this is possible, there's a problem. If this is a CNN that has 50 layers and the layers have tons of neurons, then this one layer would end up having possibly 1 million neurons. Imagine, as a big thing. And also what does that do? Just in terms of computing power, well, you're going to have to do a matrix multiplication between this and that. That's a lot of resources. Do you guys see that? So that's one issue. The other issue is that actually the relationship, although this is possible, there's a growth, an exponential growth also. That is to say, you can't just take these neurons of size n, right? Now you would have to take these neurons but of size m, where m is much bigger than n. Does that make sense? So it's not just even copying these 3, but it's copying these 3 with more neurons. So you can make it, so this is depth and this is width. You can increase the width, but it's possible to have one layer, but the move of the neurons is not linear, let's say, more exponential. So that means that whereas these are size n, these are size m, the number of neurons, and this just implies they are much bigger. Not just bigger, much bigger. Does that make sense? All right, so I wanted to kind of clarify that one. And in general, you can read through the 3 papers. I just trust them, so we're not going to have to prove that any of that is true. But basically, it does kind of imply that, one neural network can do it, but it doesn't make sense. So this is better for constraints and also in terms of the amount of neurons, basically. So depth is a good thing. Okay. All right. So that's kind of one of the things I wanted to say. This is the preferred way. But you can read through those papers historically, and this just goes back to this idea of the universal function approximator, which basically means, any function can be approximated by a neural network, right? So, what that kind of implies also, let's say that you want to build a quadratic function, or you could just build a a function that is made by a neural network, because you remember a neural network takes inputs and outputs, right? It'll figure out some structure. It can approximate that one. It can approximate a polynomial function. It can approximate, and in fact, the theorem says it can approximate any function you can think of. So in theory, do you have a theory about giving it stock prices now and telling you what you should buy or sell? That's a function. Do you see that? So the implication of that is not just, geometric functions like these. Remember that a function is literally any input that's processed, transformed, and gives you an output. So it's got very big implications as to what that actually means. However, they do constrain it in saying, okay, within this scope, but there is a higher implication there, that it can approximate a lot of behavior, because at the end of the day, machine learning is just inputs that go into a network, and then you get outputs, right? And you have to train them. Does that make sense, guys? Any questions on that? All right, so you can read those papers, if you're bored, they make a really good read. And they're definitely the classic papers on the universal function approximation, basically. All right. Okay, so today then, that's kind of what I wanted to start with that. The topics that we're going to be discussing this week are, so this week is definitely a theory, but it's a foundations, set of lectures. In particular, we want to learn how neural networks learn, right? That's where we're going to start. Okay. So I'm gonna give you guys also an assignment that is actually bonus points. So it's not an assignment that's required, but it's a very nice proof that I want you guys to try to do. And whoever does it, will get bonus points. Okay. This should be, so I'll lay out a lot of it. Hopefully you guys can. When I mean proof, I mean you have to like implement some code that shows that it works. Okay. But we'll talk, but it's bonus points. It'll be worth a lot. I will say that because it's hard. All right, and you'll have until the end of the semester, but I wanna lay out a lot of foundational work before we get to that. Right. What I can tell you is that the proof basically has to do with how neural networks learn, right? And it's gonna be that mechanism that we have to study. Okay. So we're going to start, as we start with as I said, I'm talking a little bit about history today, but as we talk about neural networks, we're going to start at the beginning, right? The foundations of neural networks. Probably the easiest thing to understand is the perceptron, okay? In some of these lectures and labs, the coding part that we're going to do, we're going to use Keras, of course, but to really understand everything that's going on, we're actually just going to try to build it from scratch. Does that make sense? Now, does that mean that like with KNN, right? Does that mean that you should build a neural network from scratch? Probably not. I don't recommend that, right? You should be using TensorFlow and, or PyTorch. So we'll be using definitely, it's like in parallel, right? I'll be doing things in TensorFlow, but also I want to do some things in NumPy. In particular, the very first algorithm called a perceptron, okay? And that's why I'm going to talk a little bit about history. What I like about the perceptron is it should allow us to see a lot of how neural networks work and how they learn from scratch in a very easy to do thing. Does that make sense? All right, so perceptron will be the first thing that we will talk about as far as Thursday or at the end of this day, and then after, and Thursday. Okay. So we'll start there. So let's call this set of lectures. I'm gonna call it light neural networks. Okay. What I mean by that is I'm just giving you the very overall right now so that you're aware of a lot of the terminology, right? And how things fit together before we actually dive deep into each one of these. Okay. Now, none of this is super hard. It's very like, I should say, like very intuitive. It makes sense, right? Yeah, that's it. In fact, what I would say is that students, once they go through this and they learn it, they're like, is that it? Really? Right. And so that should be because there's, surprisingly, there's only one mechanism to train neural networks. That's the amazing thing, right? You would think there's like 100 hundreds, and there's only one that everybody uses, which is called stochastic gradient descent. So we're going to explore all of that and go into the details, okay? But just take these as light neural networks. Probably the code on Thursday will be the perceptron, linear regression maybe. We'll begin with that. We'll talk a little bit about the math behind it, but whenever I do anything with math, I'll write the equation and then we'll write the code as well. And it's usually very easy to get things in code. All right, so let's go ahead and go over here. So I'm calling this light, neural nets and history. And as I said, I like to tell the history of neural networks. I happen to like it a lot, and I just think it's very important to understand, how this has evolved, right? All right, so before I begin, I guess, are there any questions? Anything? No issues? All right. Yeah, and also I had a student that had a problem saving files, Jupyter's to PDF. Have any of you had that problem and fixed it somehow on Windows?
I did end up fixing it,
How did you fix it?
installing a lot of things, but then when I tried it today, it didn't work anymore.
Ah,
So I don't know, you can say Control P and then it'll give you the
print it to PDF.
Save this PDF.
Is that what you're all doing?
Look at good.
Okay, is that what you're all doing? You fixed it. But did you had to install some
It wants like handoff and link.
yeah. So you just saved it to HTML and then do what? Print it to PDF or something? And is that what you're submitting, an HTML to me? Okay. Yeah. Okay. Yeah. Okay, but if you can do that print and print to file PDF, I guess that's fine. I'll have to look into how what's the mine worked. I saw something. You're all using Windows, correct, for the most part? All right, let me look into it because it should work. All right, but I wanted to ask that question, so I'll work on that. All right, so let's get started. All right, so let's start with machine learning. Machine learning, traditionally, like 15 years ago or something, people would divide it into just two areas, supervised learning and unsupervised learning. Now I should say there's more classifications that are quite interesting. So I'm going to start there. We still do supervised learning. This is the bulk of the class. The bulk of this class is supervised learning. There's also unsupervised learning. I will cover this towards the end of the semester. It takes a week. Unsupervised. This is, we have KNN in supervised. In unsupervised, we have something called K-means. It's an algorithm. I'll explain how it works, but the intuition is similar to KNN, all right? Just what's the difference? Supervised, you have the X and you have the Y, correct? What do you think we have in unsupervised? Just the X. There's no Y. So we have to learn something about the data, but we don't correlate data to outputs. Do you guys see that? So, but it's got its uses, and I'll show you some interesting things that you can do it. I mean, it's a type of a classifier. It's just that it classifies whatever it wants versus, what you tell it to classify, because what it looks for is things that are similar. And you just tell it, I want 6 things that are similar. It's going to find 6 things that it thinks are similar, and it's going to give them to you, right? So it's sometimes useful, sometimes not useful. Does that make sense? All right, so the other one we're going to cover is something called reinforcement learning, RL, right? So we'll be covering this probably as soon as I finish neural nets. I'll throw that in. Shouldn't take that long. Reinforcement learning is very interesting because you learn by doing. So you build a model. Basically, the best place to think about reinforcement learning is games. But I should say, if any problem in the world that you can think of, if you can model it as a game, you can use reinforcement learning, right? And so the trick is this. Let's take a game for sure. And maybe in your 265, you may have already touched on this. I don't know, because that's an AI class. But, Sorry? Pac-Man, so you guys did touch on it? Yeah. So basically in reinforcement learning, I'll do also like a game here just to kind of illustrate how that works. But in reinforcement learning think of a game, like the game of chess or, any game really, Atari, right? Your Atari games, if you've ever. So what happens in something like Atari basically, or chess, right? Let's think of Atari. You shoot and you destroy something, right? And then in another situation, you shoot and you don't destroy the thing that you were, let's say that's a destruction. So what the model, because it's playing a game, right? It knows what's going on. The game is keeping like a tally or a score that tells you, here you got a point, here's like a -1. Do you guys see that? In chess, it's the same, right? So if you lose a knight, bishop or something, you're in trouble. And if you win one, you're up. So the game has these rules. You play it in a loop, basically. You're trying things out. And as you're trying things out, you're trying to learn what to do. Do you guys see that? So it's a type of supervision in the sense that the rules of the game give you feedback, either positive or negative. Got it? You know, you take all these actions, you're shooting just, let's say you're in an Atari game and you're just stuck here shooting there, you're losing points, right? So the game is letting you know that. So you need to try something else, right? The key with RL is that you need to represent everything as a states and actions, right? The easiest way to think of reinforcement learning is to create a table. It's where you should start. And the table basically tells you that on the left side, you have states, and on the right side, you have actions. Do you see that? And you need these values should be random initially, but as you're learning the game, you're learning what these values should be and which one you should pick. So you can think of it as a type of a weight. For instance, I'll give you this example. Let's say that this state represents somehow, and you got to really think really hard of how you're going to represent states, okay? And the easier the game is, the easier it is to represent the state. The harder, say a self-driving car like a Tesla, that's a much more difficult state representation, okay? But possible, certainly. All right, so let's say that you're this space invaders, you're this ship, and you're stuck on this side, right? That represents that you're on this state. Do you see that? That state represents that you're here. So now the actions are what? In Space Invaders, what do you do? What does the ship do? Move left? Move right? Does it move back? No, right? It's always going forward, correct? Because the things are approaching it, so I assume they're... And what else can it do? Shoot. So you can shoot, not shoot, left, right. Do you see that? Are there any more actions for Space Invaders? Probably not, right? That's all it can do. So what you need to learn... Oh, yeah, please, sir. Yes, I would. I mean, because don't you in Space Invaders have a limit of how many bullets you can shoot? Yeah. Is that not a thing? So if that's a thing, that's certainly important. Because if you just get stuck here and fire all your bullets, you're done. You see that? So then, yeah, that's a good question. There's the fourth action. You just think of all the actions that you can take, right? So if you're stuck here, what's probably the best action to take? Go right. Do you see that? So since this is the state or represents this position, you know, this value, let's say that represents go right, should be what? High. And the other one should be 0, basically. So that every iteration, you look at the state that you're in and you pick the one with the highest value. In this case, because you're hitting the wall here, you should probably move to the right. Does that make sense? You see that? And eventually you pick up the other ones. You know, when you're in this state, you know, what's probably the state where you should fire? Just as an average, the most likely. It's difficult to say, but in the middle probably, because that might improve your odds if you're coming from the left or the right. Got it? So anyway, I'm just throwing this is light neural nets right now, right? So I'm just throwing these ideas at you. We'll spend some time and take a look at the code on how to update this. There's something this is called Q learning. This is the Q table, and there's an equation that allows us to efficiently update these values, call them the weights, and that's going to be called the Bellman equation. So we'll talk about all that. We'll go over the code, and you can also, this is just a table. Q table is just a table, no neural net involved really, but we can also build a neural net to represent this. Why? The universal function approximation theorem says that I can approximate pretty much any function, including this. So I'm going to approximate it. Do you see that? All right. All right. Any questions on that idea? So that's, you know, right now I'm just talking about classification of ML. So we got supervised, unsupervised, reinforcement learning. It's a type of supervision, but you don't have labels, right? You don't have to actually go and create all this data. You just need to model your problem as a game and then find a way to get that feedback. You see that? I mean, this is like a nuts example, but if a Tesla has a bumper that moves, when it hits a person, that thing moves, right? That's a feedback that says you should not have done that. You see that? Obviously, that's probably you're gonna get sued. Yeah. but you see that. So definitely with reinforcement learning, you have to do this in a simulator. That's the other thing. You need a simulator. Okay. But I'll show you, I have a simulator, for instance, called AI Gym, and we can model a lot of two-dimensional games. There are ones that do 3D games, or you can build your own, and I'll kind of give you some intuition on how that would work, okay? But as I said, after we get through neural nets, that will be the topic. All right? Any questions on that one? So in your experience of knowing machine learning, do you know of any other classifications? Ways of classifying machine learning. We got supervised, unsupervised, reinforcement learning. This is definitely an exam question, so better understand this. What's another one? Deep learning is basically, you can use it for supervised, you can use it for unsupervised, you can use it for RL, right? So I just said that you can represent this as a neural net, because neural nets are universal function approximators. They can approximate a lot, if not all, everything, right? So, but can you think of a fourth categorization? Yeah. Where did you get that? Yeah, okay, all right. That's very good. Yes. Semi-supervised. Okay.
I think I heard you talk about it.
Did I? Okay, yeah. Semi-supervised. You're right. Yes. So what is semi-supervised? Anyone? Semi-supervised? All right. Have you guys heard of something called ChatGPT? It's all the rage, right? ChatGPT is a transfer learning LLM, very large language model, LLM. Yeah, that's Bing's AI, right? So this is based on this thing called GPT-3, which is based on GPT-2, which is based on GPT-1, which is based on a deep learning technique called transformers. Right? This is also based on an idea of transfer learning, but transfer learning is not semi-supervised. Transfer learning just means that the folks at Google or the people at Facebook, Meta, they train these models with huge amounts of data, super, GPU computers that have 16 GPUs in the motherboard, all working together at the same time. Computers that cost 100,000 or more, right? And ran this for a month, okay? To learn the weights, which is what we're gonna be, the perceptron also learns weights, right? The neural network that we're gonna build today, called a perceptron, or in this week, learns weights. ChatGPT is a transformer based on neural nets that also learns weights. We saw in Keras a few days ago that if you print the summary, you get the number of weights. Do you guys remember that? And I increased the size of the neurons and got like 32 million weights. I haven't checked what ChatGPT has right now, but it's probably in the billions of weights. You can Google it, and I'm sure it'll tell you the number of weights that it has learned, right? Meta, apparently, or Google, or both, have proven the following: that as long as you make a neural network that's bigger, so that means bigger architecture, and you feed it more data, it's going to perform better. That's crazy, right? Do you see what I'm saying? Like, I don't know how experimentally, or if actually it's an extension of the universal approximation theorem, but they basically said these large language models, give them more architecture. That means make them bigger and give them more data, and they'll get better. That's what they've been doing. They did they did GPT-1, gave it architecture, gave it data. GPT-2, larger architecture, more data, got better. GPT-3, more architecture, more data, got better. ChatGPT, I believe, is GPT 3.5.
Apparently,
Huh?
3 has 100 billion. GPT-4 is expected to have 100 trillion.
100 trillion. You see the jump there? That's like exponential or above. And basically, they're just saying the more architecture, the more data, the better. That's a problem for us because I don't have a computer or that amount of data to train my own GPT. So machine learning used to be in the hands of everyone. Anyone could do it. And now, unfortunately, it's starting to get to the point where only they, Google and Facebook, can do it because only they have the resources to do it. Yeah, go ahead.
So you're saying like even the hard.
Exactly. Well, what they're saying is you increase the architecture and you increase the data, it'll get better. That's what they're saying. That's, this is kind of, these are current things. So I can tell you this is what everyone's believing right now, which is surprising, right? They give it more architecture, more data. A GPU costs $4,000 to $5,000, like a GPU box with one GPU. What they have has 8 GPUs or whatever, special GPUs, hundreds of thousands of dollars. But even if you have, let's say that you have wealth, right? And you can just spend on this computer for fun, you still need the data. Where are you going to get, I think Roberta XLM, which is the one I remember, was trained on 2.5 petabytes of data. That's a lot. I don't know what GPT-4 will be trained on. Probably a lot of data.
At what point does quantum computing start?
When it's invented, doesn't exist. They're making breakthroughs. I agree, but quantum computing, I think, can only solve specific problems. It's what my understanding. Someone else may know, but I don't know much of it. But my understanding is it can solve specific things.
Obviously, the computer and layers of quantum bits, which you can have 2 quantum bits and bits that actually more. But
no, I always think of it as, whereas we need as we will learn, gradient descent, right? Gradient descent can't. So let me put it this way: we need weights, correct, to have a model. I mean, in theory, we could just randomly select weights forever until the model improves. What's the problem with that? Selecting weights randomly is probably not a good idea. We don't do that, thankfully. We have something called stochastic gradient descent. Is an algorithm that does what? Intelligently selects how to update the weights. Do you guys see that? That's what we will be learning about. It's a very important thing. Without it, we would not be able to do machine learning. To take this analogy to your question of quantum computing, maybe quantum computing, because of all this computing power, could guess all the weights in one shot and see which one does better. Do you see that? But I don't know how close we are. It's one of those technologies where we're only either 5 years away or 50 years away or 100 years away. It's not clear. Okay.
Apparently, GPT-3 was only trained on a little bit less than 600 gigs.
600 gigs of data. GPT-3?
500 gigs.
Yeah, it's possible. I mean, but they're getting bigger. So anyway, so going back, so I kind of got away there. So semi-supervised, right? That's what we were talking about. So the question is, you have to give these large language models, right, 2.5 petabytes of data. If they were fully supervised, what does that mean? We would need to give it the text, right? Because it's a language model, so it's learning text. And we would have to train it, right? We have to give it the X and the Y, right? Imagine annotating all of those sentences with labels. That would be impossible. Do you guys see that? But at the same time, semi-supervised means we do have this and we have that. So then how are we getting this in correlation to that? Do you see that? That's semi-supervised. We do have it. Basically, we do have it, but it's not difficult to get. Like regular supervised learning, you think, iris, setosa, virginica, you have to look at those plants and label them, right? That's supervised. Semi-supervised, we still have X and Y, but we don't have to label it. So how are we getting it? Well, as it turns out in language, it's easy to get because we have a lot of language. So I have the cat is sleeping on, like that. You see that? So this is the input. This is the neural net, right? The transformer. And the output is the cat is blank on, and then I could say the bed. Oops. On the bed. Do you get how it's semi-supervised now? Guys? This is the input. This is the output. So this is the X. This is the Y. What it learns to do is what? Fill in the blank. So think of it this way. The cat is sleeping on the bed, and it predicts the cat is, well, eating, I guess, could be correct, but it's got a lower probability. The cat is flying on the bed. That's not correct. Do you see that? But when we do the training, we gave it millions of these sentences, right? And so it's going to learn that it's more likely that it should be sleeping. Do you guys understand? Is this easy to get? Yes. I mean, it's literally the same sentence. So we give as input the sentence, and we give the Y also the sentence, except that we take out words. So that the machine learning algorithm needs to learn that word. That's semi-supervised. There is an X and a Y, but it's something easy to get because we give it the same thing as both input and output, where the output is missing. It's got blanks. And so it's basically doing fill in the blank. Any questions on that idea? All right, so that is semi-supervised. So in semi-supervised, we do have X and Y, but they're easy to get, right? Like in text, for instance. All right, so anyway, that's the classification of neural networks. Okay. So for neural networks, as I said, this is just light and terminology. So what are the algorithms involved? So the algorithms involved. All right, so what this means is, to implement neural networks, which is basically what? A neural network is an architecture set of neurons, other neurons, right? What we need to learn is the values of these, the parameters, right? The weights. That's what we need to learn. And that's why we're going to start at the perceptron this week, because it was basically the very first neural network in a sense. And so we're going to go through the whole process of how it is trained, and it should be able to classify, actually. Okay. Right. And that should give us a lot of the intuition. But to do that classification, and in particular, the classification of deep neural networks, there's an algorithm called gradient descent. It's actually called stochastic gradient descent. Okay. This is something that we will talk about later, stochastic gradient descent, but it's a very important algorithm without it, it would not be possible to train neural networks. Okay, there's a very interesting, very like interesting technique, right, of how it works, but also very mechanical in how it does what it does. Okay, and that stochastic gradient descent actually has several algorithms that were invented for it to work. Right, we're not going to get into all that depth. Also, I should stress, even though we're going to discuss this and we will do some examples, the reason why PyTorch and TensorFlow were invented is so that we don't have to do this. So this is the one part that those frameworks actually abstract completely from our view. We just kind of have to learn how to code it, but they actually do that whole processing. Okay, so stochastic gradient descent is done by TensorFlow and PyTorch efficiently, very efficient. All right. However, as I said, we will cover, the elements of the algorithm, which are not super complicated. Okay. Any questions there? All right. So there's going to be this idea of the feed forward algorithm and then the back propagation algorithm. All right. That implement all of this. And at the end of the day, everything in machine learning revolves on guessing these weights, or not guessing, but actually optimizing for these weights. Got it? All right, so we will look at that. So that means we're going to need to have several steps, including a little formula that allows us to update the weights, which is called the update rule. And we will talk about that. But just as I said, just to kind of give you an introduction, we have the weights, right, that we want. And then we have the current weights. And then what we do is we need to update them. So what we do is we take what is called the learning rate, which is a value that we multiply times another value that we get, which basically gives us direction. So what that means is every time we're updating the weights, we need to know if it's a plus or a minus multiplied times some value that you choose. And then what's going to be the effect of that on the weights? If we do something like this, I'm just generalizing it right now and not telling you how to compute it, but this is how we update the weights, right? So what are we doing here? Every iteration, if we get a positive times this, what happens? Huh? Decrease, right? Is what you mean. You decrease the weights. What if it's the next iteration, it's a negative? We increase the weights. Do you see that? So this is the little game that we're playing, right? To update the weights. We don't just randomly pick, oh yeah, I'm going to add any and see what happens, because that would affect the network. Instead, you have the weights, and then you decide that you're either going to decrease or increase the weights by a specific value. This is really important. If you pick 0.000001, I can tell you it'll never find the weights, because you're increasing or decreasing the values by too little. You see what I'm saying? The other thing can happen is if you make that too big, it never quite arrives at the good values, because it's the changes are just too drastic. Do you see that? All right, so all of this will be studied within the context. We're going to basically do this several times as we go through the perceptron, linear regression, logistic regression, multi-layer perceptrons, and deep neural networks, okay? So we're going to, but it's always the same mechanism. And all of those are only different in the architecture, which means this, right? How many inputs, how many hidden layers, how many outputs. That's called architecture. But the mechanism is always to do this. To go back to your quantum computer thing, we wouldn't have this. We would just do all the pluses and minuses in the universe, but that can probably be a lot, right? But if a quantum computer could do that in parallel, you don't need stochastic gradient descent. But until we have that, we can't do that random. So we need to do it in a smart way. So the question is, if this is fixed in mostly, how do you decide if it's plus or minus? Do you see that? That we have to study how this is done, okay? This is the stochastic gradient descent algorithm. And like I said, the proof that I'm asking you to do is bonus points will also relate around this idea, okay? But I have to give you a lot of background for you to kind of get what we're talking about. Do you have any questions? on this? Pretty easy, pretty clear. All right, good. So that's kind of where we're going. So we'll talk about that. But as you probably understand by the intuition or know this, you know, what happens here? You have some inputs, they go through the network, and you get some outputs, correct? Yes. And this is, let's say, a hidden layer. So you get some inputs, they go through the network, you get an output. What's going to happen if you have really bad weights? Get bad outputs, right? That's kind of what happens. What do you do with these outputs here? If you haven't learned, what should you do intuitively with the outputs in a supervised learning problem? Compare them to the real values. Do you have real values? Yes, right? That's the whole point of having a train set. And when you have so let's say you have the pred, either a vector or a value, and the real, what do? You take the difference, generally speaking, right? So if you get a 0.5 here, and then you get a 0.8 over here, that's a difference of 0.3. What if you guess 0.01 and this is 0.8? Which one of these is a better prediction? Huh? The top one, right? Because it's the one closest to the real value. Do you guys see that? So that's what we do in machine learning. We predict, we compare to what we have. We take some metric, some measure of closeness or whatever you want to call it. And then based on this result, which we'll study this in more detail later, we back propagate. Back propagate. So that answer back propagates to update the weights, which is this equation. Do you see that? But this difference has to work itself into that somehow, right? And that's requires a little bit more. Do you see that? But that's how it works. It's simple. I mean, it's actually pretty simple, right? You know, what happens in the next iteration? Take the input, feed through the network, get some outputs, compare to the real ones, get some kind of a difference or something. Then maybe there's something in between, but feed into this, update the weights. So obviously, this result has to help you to decide how to update the weights. And once you do this, eventually these weights will be pretty good. These predictions will be almost exactly like this. And then the weights change very little and your model is trained. Got it? All right, that's the general mechanism. All right, so we will take a look at that later. Okay. All right, so now we're ready for the history. Okay, so we're going to talk about the history. This is really, I think you'll find this pretty interesting. I'm only going to do history today, but pretty nice history. Okay, so the big names in machine learning are Rummel. Well, those papers certainly that I provided. Take a look at those names. There's none of this would be possible without an optimization technique, backpropagation. That's the famous 1986 paper by Rummelhart, Hinton, and Williams. Do any of those names sound familiar? None of them? In particular, Hinton, that's Jeffrey Hinton, is basically the grandfather of deep learning. So it's like the guru. Okay? Yeah, but that paper is pretty important. That's the algorithm of gradient descent, which, like I said, without it, unless we have a quantum computer that randomly selects the weights, we would not be able to solve a neural net. It's very interesting how they do it. Okay. All right. So the history, I'll do like a timeline. Okay. And so we will start. A little timeline here. All right. So obviously everything builds on top of everything, right? So we've seen already what was that theorem that we saw initially, the triangle one? Beginning of the semester, we saw a formula. Well, starts with a P. Huh? Yeah, right? When was that dated from? I don't know, but that's math way back, right? Yeah, or the Greeks, right? So those are pretty old things. So what I'm trying to say is, obviously, a lot of math came before what I'm discussing, right? Because we use that, right? Pythagoras, right? Pythagorean, yeah, theorem. What is it in Egypt? Wow, yeah. So so that we used to calculate what? We used it in the Euclid, in calculations, right? In the triangles, and then we have the Euclidean distance, right? We also Euclid, I guess, right? All of those things can be used in machine learning, right? So there's quite a bit of background in math, obviously. So I should say before the, since the beginning of civilization. But this discussion will start in the 1940s, okay? So it's more of a related to just neural nets in general and not just KNN and all the equations. So it kind of starts in two places, right? It starts at Bell Labs. So do you guys know where Bell Labs is? New Jersey, right? It used to be in New York and then New Jersey. Bell Labs. So you guys have heard of Bell Labs, I assume. You have not heard of Bell Labs. You know that everything was invented at Bell Labs, right? Some people would disagree with that, but a lot of things. One very important thing that was definite, that's a joke, but one very important thing that was invented at Bell Labs is the transistor. Transistors are what make computers possible, right? And so that definitely is a very important thing because we would not have computers without the transistor. So yeah, Bell Labs is AT&T, I think. It used to be called Bell Labs. But again, going back to neural nets, two important people are Rosenblatt. So you saw, Rosenblatt here. Rosenblatt. So this is the person that created the perceptron, okay, which is the algorithm that we're going to discuss, this week. The perceptron. It's kind of like the first neural network. Yes. All right. So that was around the 1940s. So I think they still had now, because the transistor was just then being invented, right? Which is the little chip. They were using what? Like the vacuum tubes, I think, and relays, and still they were kind of building computers that way. Do you guys see that? But around this time, obviously, came the transistor. I forget the name of the person that invented that. You can look it up. Alongside there was also a gentleman named Claude Shannon. Have you guys heard of Claude Shannon? Basically, is the father of information theory, right? So actually, your major, IT, which is based on information, that's kind of Claude Shannon. So Claude Shannon did a lot of things, invented information theory, obviously, which is somebody told him to coin a metric called the bit. Do we use a metric called a bit? Yes, right? And that's where it came from in the 1940s. Claude Shannon is like an eccentric guy, worked at Bell Labs also. And very funny, he would ride a what do you call it? The ones that only have one wheel, the bicycle. What is that called? Unicycle. So at Bell Labs, he would ride a unicycle in the halls of it. That's how eccentric he was. Okay, they just kept him in there, gave him an office, and just told him to do whatever he wanted. I'm not kidding. And while he was not doing anything, he invented information theory for AT&T. All right, so, Bell Labs. Anyway, so very interesting guy, invented that. Then he got bored with information theory and he switched to cryptography. So he kind of invented cryptography also. He's the first one to define what makes a secure cipher. If you guys take 350, which is the crypto class, we'll talk about Claude Shannon. All right, and then he got bored with that once he had invented everything. And he decided that he was interested in AI. So he invented the very first, you can look this up, it's in a museum. The very first like AI game, I guess, which was a robot mouse, which was nothing more than a magnet. He built a labyrinth, and the robot had to figure out how to traverse the labyrinth to find the cheese. The thing is, you know, you can get lost in a labyrinth. So the goal was for it to just try it, learn, and eventually just get to the cheese without trial and error. Does that make sense? So that's Claude Shannon. So it's called a robot mouse maze. Okay. So maze. So robot maze. Okay. All right, so this is in a lab somewhere, you can look it up. All right, so that's kind of where they were in the 1940s. With, like I said, Rosenblatt. Somewhere along there, like in the 50s, came Adeline. So it's an algorithm supposed to be a little bit more advanced. Then, really, between all the excitement of the perceptron, don't forget that's the start, by Rosenblatt, and maybe around the 1980s, we had what is probably called the first winter of AI. And what that means is there was a period of like deadness. And this was thanks to a gentleman called Marvin Minsky and a paper he and another person wrote, which was misunderstood. And basically, without getting into too many of the details, what Minsky did is he said that neural nets in a specific configuration could not solve a lot of problems. But then somewhere in the paper, there's a comment that says, oh, but if it's a multi-layer perceptron, then there's no problem. But somehow, I'm not kidding. I tell you this because although it's not relevant to stochastic gradient descent, I think it's relevant for you to see how AI sometimes is a lot of perception. Sometimes there's a lot of hype. Sometimes there's a lot of realism. The algorithms work fine, but people lost interest because they basically just read the first page of Minsky's paper. And this is a true story. And so a lot of people just didn't continue working on machine learning or neural nets because they felt that it didn't have what they needed, okay? Also, obviously, they had just invented the transistor, so there was very little that they could do, honestly. But this influenced things quite a bit. The next big pickup, I guess, was around this time, as you saw in the what I said around 1986. Backpropagation came out, the paper. It's called, sometimes people call it backprop. That's the algorithm that we're going to learn about a lot in this course, which is the one that allows you to learn the weights efficiently. Okay, very, very interesting. And this was, as I've already stated, Geoffrey Hinton. Geoffrey Hinton was one of those people that he didn't care about what Minsky said or whomever, right? It's just one of those people that have a passion for something and just do it, right? Doesn't care if it's going to work or not. They just wanted to work on neural nets. So he's got in the 70s, I think, like the first Ph.D. in AI. They just made it up for him, right? And that's how intrigued he was. So that's Marvin Minsky. Geoffrey Hinton. He's a professor, still alive, at the University of Toronto, in Toronto, Canada. He's a British fellow, came to the United States. All the funding was in military applications, did not want to work in military applications. Canada offered him, like, do whatever. And so he went over there to the University of Toronto. Basically, all of his students that went into his classes, have had a lot of success. All right, so that's Geoffrey Hinton in 1986. So this takes us to around 2000. But what was happening here is computing power was improving, right? You guys probably remember some of these computers, maybe a little bit before your time, but you know that there were computers around this time, right? In 86, in the 80s, there were computers. There was the internet already. So there was a lot of excitement there. But because of kind of this Minsky paper, still, people thought neural nets are not great. And a lot of people did not work on neural nets, except for Minsky. I keep saying Minsky, except for Hinton. So Hinton was the kind of person that would go to conferences. And at conferences, you usually have these dinners, and he would just get like the worst table. Oh, those are the neural networks, guys. We're going to put them in the back of the con. This is true story. I'm not kidding. All right. But they kept working. They obviously invented or developed a stochastic gradient descent, that paper from 1986. And we're leading up to something, right? So there was this darkness. People just wanted to work, the KNN, right? There's other machine learning algorithms. People were doing machine learning, but they were just not doing neural nets, right? Because of all this, like, it's not clear how they work. They don't work. What's going on. But anyway, my point is, Hinton is a good example for you guys of persistence. And this is me just being like, if you have a passion, follow it. Even if people hate, laugh at you, if you love it, eventually you could be the next Geoffrey Hinton. Oh, the story about Google is very, very interesting. Geoffrey Hinton is a professor at Toronto, right? When he became all famous, Google went to the University of Toronto, offered him a ton of money, moved to California. Google, we'll give you whatever you want. He said, no, I like Toronto, Canada. I'm happy here. You know what Google did? They built the office in Toronto. They brought Google. I'm not kidding. The second Silicon Valley in North America is in Toronto, after California. Why? Geoffrey Hinton. This happened. I mean, this is a story. They tried to recruit him, but he just didn't want to go. He'd been a professor at Toronto. Toronto's pretty, I've heard. So he just didn't want to move. They built it around him. I think they built a building around him. They gave stuff to the university, and then eventually he kind of just accepted. Okay, and that's it. That's pretty much how it happened. So this is a very true story, but we got really ahead there. So what is really the event that changed everything? So you can see that Geoffrey Hinton was working hard. Other people, obviously. So the paper. He didn't write it alone, right? So there was Rumelhart, Williams, there were a lot of people working on it. And also people would just stumble to the University of Toronto. Hey, there's a neural networks class. Would go in there and it's with Geoffrey Hinton, right? So they're the only ones in the world doing this, because other universities are, nah, that's not, we're not going to do that. You see what I'm saying? This is a great example of persistence. But anyway, so they were building all the algorithms, all the techniques with the computers that we have today, right? They wanted to build deep learning algorithms, but computers couldn't really. So now we're getting to the point where all the framework and all the algorithms are kind of built, but the computing power was still not there. But something happened. There's an event that's like changed everything. And that happened around 2007. In 2007, NVIDIA came out with their, believe it or not, with their GPUs. The GPUs that finally made this possible. Made like actual deep learning, a GPU with however many GPU processors it has. And that in 2007, we get that's really a thing that is really important in history. Why did NVIDIA create these GPUs? Not for machine learning. They built them for video games, right? That's what these things were for. Do you get how GPUs for video games can also be used for machine learning? Do you guys get how that works? All right, so if you think of a computer game, right? First-person shooter or whatever. Imagine me, I'm a mesh, right? In that 3D space, correct? In linear algebra, we know that if we want to move something, stretch and rotate something in a vector space, what do? We multiply it times something else. It's classic like thing. So you have a matrix, multiply it times a vector. That's a stretching and rotation of it. That's it. And so in video games, let's say I'm a mesh like this with the gun, right? I'm not going to move, but I'm not going to like a game with the arms, or what I mean is it's not going to move the arms. I just want to move to Gang Rock, right? Where you are. I want to go over there. in that vector space. I'm a mesh, which is basically I'm a matrix in that space. Find the vector that when you multiply me with, it moves it. Because, as I said, that's what linear algebra does. Matrix and vector multiplications, by definition, they are stretching and rotating operations. That means it moves and, you know, that kind of thing. You just have to find the right values to do that. Well, in machine learning, as you learn in NumPy, right, when you did your NumPy things, what were you doing? Matrix and vector multiplications, yes? Were you not doing the exact same thing? Except that in video games, it's like 3D kind of a thing, and machine learning is higher dimensional space, but GPUs are made for that. There's no limitation. And so anyway, is that clear for you guys? Do you kind of get what I mean? Yeah. All right. So GPU basically, if you get confused, the mesh is, or the rendering is the matrix, the mesh, and then you want to move it to another location, multiply times a vector, boom. It physically moved. Why do you want to do that in a GPU? If you do it in a CPU, what's going to happen? You have to multiply like this, right? You have to go with, you know, multiply the top and go down. So when it renders in the game, you see this shape, right? What do you want? You want the whole thing to move at the same time. You do the multiplication in parallel. Do you agree? And now you don't have, what is this called in a video game? Like a jittery effect, or I don't know what you call it. Lag, maybe lag. You don't want to see that lag. They were fighting that lag in video games, and they built the hardware. So obviously this hardware does that parallel operation. Just think of it. It sends the feet at the same time as the head to where it needs to go. That's what they were getting at. And it didn't take very long for these guys at the University of Toronto to see, hey, wait a minute. That's the exact operation that we're performing, matrix and vector operations. NVIDIA made available something called CUDA around 2007 as well. This is the C++ library that allows you to control the GPU. Like literally you write the code in C++ CUDA, and you get the GPU to do things. It's actually very hard to code in this style. Okay, it requires serious parallel understanding. Okay, so in 2000, but you know, they were up to the challenge at the University of Toronto. So the next time that we kind of hear about them is in 2012. So about 5 years took place between these GPUs. Probably they made their way into the University of Toronto, Geoffrey Hinton, their teams, a few other teams around the world. And what happened in 2012? This is the moment that everybody became aware of deep neural networks. Okay? What happened in 2012? What do you think happened? Oh, there's a movie about that. I don't think that's related. What happened in 2012 is there was a competition. There was always a competition, not just in 2012. There was a competition yearly, which basically they had something called ImageNet. And ImageNet was a data set of 1.4 million images or so, right? And basically what was going to happen there is they had, I don't know, like 100 classes: bird, bus, car, cat, dog, something like that. So every year they have this data set, this challenge, they make the training set available, but they keep a test set that they don't share with anyone. And then they say, okay, build your machine learning tool, enter the competition. Let's see who gets the highest score, right? Do you see why the performance metrics are so important, right? When I make the joke sometimes, let's see who does better in this class, right? By measuring performance. You guys see that? Well, in 2012, one of the students, I believe, of Geoffrey Hinton built something called AlexNet. AlexNet entered into this competition and won. And it didn't win by like 1%, right? For something to be significant like this, it had to be by a high percent. So I think it was like 15 or 20%. We're talking about everyone was around probably, let's say 70% on this task. Just classifying, this is an easy thing today, by the way. But back then in 2012, not that long ago, 10 years ago, it was pretty hard. So they had to, because it was like 90 classes, and they achieve, I believe, around 85% accuracy over everyone else. The companies that were already in this space, Google, Facebook, were shocked, right? That because they have an interest for ads and things like that, and having pretty good, they want to give you an ad that leads to money, things like that, right? So AlexNet did, and this is what changed everything. So they asked, obviously, what is AlexNet? So it turns out AlexNet was a deep neural network. Had multiple layers, it had stuff. Now, I should probably mention something that in the 80s, there was a guy named Jean LeCun, because he might see this video and then hate me forever. So Jean LeCun is the director of AI at Meta. He is also a person considered very important in machine learning. He built MNIST. You guys have used MNIST, right? MNIST was built for the post office. And it basically, how letters are written, the zip code is written by hand, and they wanted to sort it mechanically, right? Makes sense. So if you put a camera, look at the zip code, boom, you send it in one direction or the other. His whole task was to do, that character recognition, like MNIST. You guys see that? Handwritten digits, the 10 numbers, 10 digits, yeah? That make up zip codes. And Jean LeCun, I believe, is also the father of CNNs, I want to say. I believe he invented them, or at least he perfected. Sometimes it's not that they fully invented something, but they perfected it, right? Well, he had built the CNN. What is a CNN? It's a deep neural network, but a higher level, beyond what we're going to study in this class. And I believe AlexNet, I bring it up because I believe AlexNet is a deep neural network that used CNNs. Okay, you'll have to, you can research that on your own. I don't remember the specifics, but I do know it was a deep neural network, probably CNN. They had the GPUs from 2007. This is the moment where this stuff really became a thing. Okay, this is where the general public started to find out about neural nets. I'll be honest, around 2014, I was still probably a little bit clueless about deep neural network, right? So I wasn't really in the loop, right? And that's really a lot of that happened to a lot of people. Okay, so the framework that you guys are using, Keras, is based on TensorFlow. Believe it or not, that was not available until 2015. That means before that, none of you would have been able to do machine learning or deep learning. You really can't without that. I mean, it makes it super easy, so you definitely want to appreciate it. PyTorch came a little later when Facebook just didn't want to use Google products, so they developed their own. And then Keras, I'm not exactly sure, but it came, I think I told you this. It was just somebody didn't want to use TensorFlow 1, so they built like a wrapper around TensorFlow 1, and then everybody liked it so much because it made life easier that in TensorFlow 2, it is now just like part of the thing. Do you guys get it? All right. So another important thing is that there's deep learning, which is kind of what we're going to spend a lot of time on here. And then there's even more complex architectures than standard deep learning architectures. That is probably outside of the scope of this class, but there's a few algorithms there. I've mentioned one, CNNs. They're like, just think of it. There's deep learning, and then CNNs just have more stuff on top of deep learning, right? And then, so that's kind of there. And then we are basically, what is it this year? So 2023. So all the rage is Chat GPT, right? That's all the rage. All right. And the algorithm that made this possible was invented. Guess when it was invented? Let's see if you guys can tell me when you think the actual algorithm for Chat GPT. When do you think it was invented? A long time ago? Recent? Huh? 2017. This is the classic seminal paper, Transformers is All You Need, by Viswani, I think. This is the thing that made this thing possible. Without this, we would not have this. Transformers solved a lot of problems. I mean, the paper is literally called Transformers is all you need. It's implying everything else is not necessary. Jean LeCun would not like that because he invented CNNs. All right, but anyway, that's kind of the history, okay, that I wanted to give you guys. And I like it. I mean, I really enjoy it. I believe it's important to understand the context of all of this is let me just finish. Pretty recent, and who knows what the future will be. Could we have another winter? We could. But we haven't had one. I mean, things are very interesting now. And so, you know, think about the thing that this algorithm changed a lot. So there may be other algorithms that will come that will change even more. Yeah.
At what point was people been afraid of AI?
When did that start? When they, I think, yeah, that's actually a really good question. Well, I think, yeah, the Terminator is like, I think, yeah, everyone has always had this idea of like the Terminator, but realistically, I think with the language models is when people started to actually really be worried about, because you know, all these are transformers, they all have bias. They all have bias. Why do they have bias? Because machine learning algorithms are biasing machines. That's literally what they learn. Do you know what I mean? They learn whatever the majority class is. Right? You give it 100 examples of one thing and 10 examples of the other thing, it just learns that 100 thing is more abundant, and that's the thing that it's always gonna do. That's biasing, right? You know, it's not fair because that's inherent in how they are. So there's all this about, you know, what they're gonna do. That this is why Bing and all of them are really nervous about releasing like Google. Supposedly they had a thing called Lambda before, and they did not want to release it because Google was in a position where it's more problematic for them if this thing starts to do unexpected things, right? Whereas ChatGPT was developed by OpenAI, kind of a small, we're not doing anything company that, by the way, belongs to Microsoft. Microsoft, because they've been trying for so long to get Bing to work without success, they saw all the hype of ChatGPT. They were very smart, actually. They let OpenAI do all this hype. They were watching it and watching it and watching it. And eventually they saw, hey, we can use this as marketing, basically. And they just said, we're going to incorporate it into Bing. They own OpenAI. They own 49% of it. So OpenAI was, do you know who gave the initial funding for OpenAI? You'll laugh. Elon Musk. Elon Musk gave the initial funding. So again, I think he's an alien probably, or from the future. Because again, Elon Musk doing something, right? So, huh?
Because when we first invested in, they had created a video game AI that could be beat. And
yeah, AlphaGo, you mean probably? Yeah. But at that point, AlphaGo was still research. AlphaGo was still just some amazing research. Yeah. Yeah. Yeah, no, yeah. He says, so he says, and yet he's building stuff at Tesla that he's not telling you about. That may be it. He may be an AI from the future. Maybe. But it's funny that he gave the funds for OpenAI to be an open source, not a company thing. But that's why he doesn't have any money in it. And he probably is very sad about that now. And he gave, but then he, I guess, gave him permission or whatever to become semi-private. And then Microsoft bought like an initial 10% of it. And then they had like AlphaGo, but ChatGPT is different. And recently, Microsoft just gave him $10 billion, I think, for a 49% stake. in OpenAI. And they, because of all the hype of ChatGPT, you guys will be the judge of whether ChatGPT is useful. I've heard it's really good at coding, and that's really interesting. And so we already, like, I'm sure all of you, when you code, the first thing you do is you Google how to do it, right? And then copy that code. Well, that's kind of what ChatGPT does, is you just write the text and it gives you the code. And so, yeah. So they've made it part of Bing now, basically, and they're going with that. But that's kind of the story of all of this. Any questions? Make sense? Yeah. So that's kind of where we are. I was gonna say something, but I forgot. All right. Anyway, so that's, I only do this once, right? So it's not like I'm going to do a history class here, but I kind of like the story, and I kind of, hopefully it motivates you, and also hopefully it's some context of the history. And the big thing to consider is there will be bigger changes. Yeah. So anyway, all right. So we're done with that. That's the lecture. All right. So now we can move on. Since I've given you the history of everything, then now, we will start talking about some of these things, obviously, right? And the things that we're going to talk about are the perceptron, right? So we're going to start there. We're going to code this, actually. And then we're going to look at back propagation and how this feeds into training the weights of a neural network, okay? So let's just we have a few minutes. So let's start with the perceptron then. No. Oh, sorry. Let me just. All right. So let's switch over. I'm out of power here. Let's switch over to computer here. Okay, and we're going to go over to the Jupyter Notebook. Whoops. The Anaconda prompt. All right, so since we don't have much time left, I'm going to take this time just to go over one standalone thing called the dot product. Can anyone tell me what the dot product is? It's a multiplication, right? It's a multiplication. And what? Right, it's a vector multiplication and added, right? Yes. Do you think this is important for machine learning? It is, right? Because we multiply the x's times the weights in a nice one shot. So there's a lot of math and whatever. We're just going to look at the code for it. And actually it's going to be not great code, right? So this time around, I do it with this approach because it's more intuitive. All right. And I want you to capture the idea of it. And then after that, you guys can go ahead and code this in NumPy, as you always should, right? Because when you're training a model, if you're performing this dot product the way that I'm going to write it, what's going to happen? It's going to be very slow. You see that? But if you implement it efficiently, it's going to go fast. Okay. All right. So pretty important. So let's go ahead and do, so let's look at the Conda environment. So we're going to wrap up class today with just a dot product, just so that we get that idea. It's an important one. As I said, I've always said in machine learning, you don't need to take calculus 1, calculus 2, calculus 3, differential equations, or all of linear algebra. There are only selected things that we need, and not everything, right? So, and so that's kind of, so whenever something is important, I can just show you in the code the operations so that we can understand it. And these are the things that might look scary, but actually aren't, okay? All right, so I'm using, I guess, Pi37 TensorFlow. So conda activate Pi37 TensorFlow. Okay. All right, so we're just gonna do this. As I said, it's important to start with the perceptron. We're gonna write it from scratch, no TensorFlow. And that's just because I want you to learn how to update those weights, okay? We're gonna go over that, all of that manually, although you should not, in theory, do it that way. All right, so now that I'm here, I'm just gonna do a Jupyter notebook. All right, good. So we're gonna just write the code for it. Go to the desktop here and spring 2023. Let's just do it here. So the code for this is very easy. And like I said, I'm doing it the for loop approach just so that it's easier to understand. Just be aware you should probably, as an exercise for you, although it's not homework, just convert it to the NumPy approach, okay? All right, so let's define the function. Oops. So the function will be, we're just gonna use actually pure Python. All right, so define a function, and we're gonna call it the dot product. Okay, there's one of those math things you see there that needs to be demystified in machine learning. Okay, so we've got A and B. What are A and B? Two vectors. What does that mean? It's like take a Y and another Y, right? And we're gonna perform this multiplication, okay? So think the X times the Y, right? You got an X, you got the Y's, you got to learn. So basically we can do something like, I'm gonna do this in pieces also. I am gonna do a list comprehension. So list comprehension, right? And so, you know, we're going to do a for loop for I in range of the length of one of these, either A or B. Imagine A and B are both a list right now, right? You know, and later on, we'll come back to the equation. I lost the whiteboard because I'm charging the battery. So once I get that back, I'll be able to, but let's start with the code. So for I in range, length of A, length of A. What is this? A and B, do they have the same size for this operation? They need to have the same size for this operation. So we just grab either A or B. It can be, you know, the X's, just think of them as if it's iris data set, how many features do you have? 4. So this should have a size of 4. How many weights do you need? 4. So 4 and 4. You see that? And so we're just going to do this multiplication here. So when we do something like this, then we could just say I, right? So that's a list comprehension. You see that? And then if I just print it, so I'm going to do print list comprehension. Okay, list comprehension. And then over here, then I need my vectors, right? A and B. So let's think of A as, well, actually, let's stick with the example of Satoshi. You know, so I'm going to do 2 times 4, comma, 4, comma, 6, comma, 3, right? And then I have B, and that's going to be 1, comma, these would probably be smaller values like the decimals, if they're the weights, but 7, comma, 3, comma, 2. Do you see that? So the 2 vectors, basically, we're going to, you know, have them there. So I'm going to do that. All right. And then now I'm going to invoke my formula. Oops. Sorry. I'm going to invoke the function. So I'm going to say print And then I'm going to call in here the dot product. So dot product. Okay. And it's going to take in A and B. You guys see that? And so basically it takes these two. Again, we're doing this idea of like multiplying these vectors, right? We're always doing this. Okay. So I'm going to run that. And I got 0, 1, 2, 3. Why is this? No. Where's that none coming from? Oh, there's no return. I'm sorry. Yes. So return list comprehension. Okay. You guys see that? So basically the function, in this case, all I'm doing is I'm printing them, right? Now, what I want to do is I want to multiply each one, right? So I want to multiply this element times this element, then this element times this element. Do you guys see that? Making sense? So I'll write the equation, and then the equation will look like whatever it looks like. But I want you to understand that this is what's happening, really. Okay, so that, and this is the famous dot product, and it's just a multiplication between vectors, a very common operation. Why? Again, video games have a mesh. I need to move it over there, multiply it times something. That operation in a vector space is a stretching and rotation operation. Boom, you move it efficiently. All right, so now what I'm going to do here is, instead of printing I, what I want to do is I want to multiply the element of A with the corresponding element of B, right? So to do that, I can just say what? A, I, correct? All right, good. Times what? BI, right? BI. You see that? And this is the equivalent of multiplying x1 times, w1, x2 times w2, x3 times w3. You can see there's a common thing there. Those are the weights being multiplied by the x's to obtain the next value of that neuron. Now we need to add them, right? So to add them up, so actually let's run this one here first. So I'm going to do that. It'll work. We don't actually need to print since I'm printing twice. So let's do that. Did it work? So it's 2 times 4 times 18 and 6, right? Yeah, so it's doing the multiplication correctly. Any questions on that part? All right, the next step in this is we need to sum them, okay? So to do that, I'm doing this in parts just so that's more obvious to see. Sorry. Let's do Control copy. Control V. Okay, then Control V. And then I'm going to sum these values. Now you can see these values are here, right? All I need to do is sum these, right? It's like 2 plus 28 plus 18 plus 6. That's what's happening. So you can simply just do a sum of them here. Because what's really nice about this is we always want to write these functions so that any vector of any size fits, right? We don't want to make it specific for like one thing, because you never know at any moment you get another data set, boom, you were in Iris, now you're in MNIST, 784 to 4. All right, so now let's try it out. You see that? 54. Make sense? Now, in terms of the equation and the perceptron, we have weights and biases, right? Which are the parameters. So the bias here would be, let's say B equal 3. I'm just making it up here. And then since this, okay, I did this outside, right? So then dot product is actually, let's just say result, right? Dot product. And then now to complete that equation that we're kind of familiar with, you know, y, I'm going to do this as a comment, y equal mx plus b, right? It's the line. We're familiar with that, but because it's machine learning and we're predicting something, we usually denote it as w, so wx plus b. You guys see that? So that basically, this w and that x are basically these two, so the dot product. So then all we have to do is, you know, y equal res plus b. Do you see how that works, guys? See how this is important to you, for you to understand that the bias is always, when you have that multiplication, that dot product gives you a value, and then you add the bias to it. You know, it's not like for every input neuron, it's for every output neuron. And then we can print the y. So then we can do like that. Do you see that? Does this make sense? Okay, so this is important. You know, I start with this operation because this is actually at the heart of a lot of neural networks and the perceptron itself that we're going to explore this week. Okay. Again, I stress, this is very important. If you implement this algorithm, because this is a part of a whole algorithm to build a model, right? And if you write it like this with this for loop, let's say that now you're going to use it with MNIST or something even larger, and you start running it, the performance of your algorithm will be affected by that choice. Yes, it's easy and intuitive, but when you're at 3 a.m. in the morning still running this, you're going to wish it wasn't like this. Does that make sense? That's why using it the NumPy way is pretty important. Okay? Got it? So for the most part, once we start implementing this in the perceptron, they will be pure NumPy as the exercises that you guys did at the very beginning of the semester. Okay? I can't stress this enough. Okay? You know, otherwise it's very slow and people don't want to use it and problematic. Okay? Got it? Any questions on this one? Let me just, I want to finish this so I don't have to do it again. So this code is done. Let me just write one last thing and then we'll wrap up the class. I was just waiting for my battery to charge a little. Don't have much, but should be enough. So let me just write this, the equation for this, just so that you're familiar with it. So I'm going to switch over to the whiteboard. Okay. All right, so that should be enough power. So that the corresponding equation to this should be, this is the dot product, right? Dot product. And usually this, you know, it's a method of multiplying two vectors, for instance, in this example. So you can think of it as A, where this is A1, comma, A2, dot, 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 AN of any size. And this is B. And that's going to be B1, B2, dot, 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 BN. Okay, so basically the definition of the function is, you know, a dot product. It's not a, so in this, there's component-wise multiplication, and then there's dot product. There's different kinds of multiplications. Okay, so in this case, this is the specific operation which you will sometimes see written as I equal 1 to n of a I. This is I times b I, okay, which basically should translate into, which is what we just did, A1 times B1 plus A2 plus B2, or times, sorry, dot, 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 plus AN times BN. Do you guys see that? We just did this in code, okay? I did it the for loop way, because I think it translates way better to this. Just please be aware that's pretty inefficient and it'll be very slow and it will affect your performance. Okay. And so why do we do that? Well, we're going to stop here with just the perceptron, which I want you to see. It's kind of that operation. So remember, this is Rosenblatt. So in this case, the perceptron is your x1, x2, ... xn, only now these are neurons, right? Neurons that basically, in terms of a neural net, give you one neuron in the next layer, okay? That's that thing that we were getting, res. And basically, we have a multiplication, just like the one we did, where these ones are W1, W2, Wn. You see that? So it's the vector of the weights, the vector of the inputs that gives you that specific value that we have, right? And so you can think of it as that's that sum that's happening. And then the additional thing is that there will always in neural networks be an activation function. So the result of this goes into this function. Do you guys see that? And we have to study which one Rosenblatt kind of invented for his time. And then you get an output. And then, of course, there's got to be some kind of weight update. Do you guys see that? So that's what we're going to explore on Thursday. So I'm done with these pages. And then on Thursday, we will just I might do a little bit of a description of the algorithm on the whiteboard, but then we're just going to code this up. And I think this, what's kind of really nice about this is that this method, everything builds on top of everything else. So like knowing the perceptron, 60-70% of a deep learning algorithm already. The simple ones, right? Remember, not the advanced ones like CNNs, transformers, but just deep learning. And you've already done it in Calix. So we're just doing it from scratch a little bit because you do need to understand some of those mechanics. Got it? All right, so I'll pause the video here. Stop sharing and end it.